Hello dear student, this is Devang Shah from LG Institute of Engineering and Technology under the LG University. So in our previous session we have discussed about the finite state machine, how it's going to correlate with the synchronous sequential circuits where we learn about a difference between combinational logic and sequential logic. Again we learn about a kind of state diagram. From state diagram how you can design any FSM is a kind of finite state machine is nothing but the representation of synchronous sequential circuits. So in a way, from that you can learn, you can understand about the different kind of states, the kind of present state, and you can go through or you can evaluate the next state based on input and output, right? So again, we'll further continue here with synchronous finite state machine where we learn about two types of FSM. So here we are going to discuss about two types of FSM. One we define as a Mealy model, another one we define as a Moore model. So what is all about? So Mealy model you can see here, Mealy machine changes its output on the basis of its present state and current input, right? Same way Moore model is nothing but is the output depends only on the current state. It does not depend on the current input. So for further, if you see this particular block diagram and then you can see a kind of Mealy machine where you apply the input, there is a next state combinational logic. That's what we learn in terms of the FSM. Then you apply this with the state register that will define a kind of next state output. Then the same output you can apply to the combinational logic, right? And final output you are going to get it where you can see this input is also feeding to the output combinational logic. So there is a direct connection from input to this way, right? And this must be required. This particular feedback of the output of this state register is again going back to the next state of combinational logic. That is always there through the flip flop or through the memory. So you can see the kind of difference. The Mealy machine, this again the output depends on the direct input as well as the present state output. Same way here Moore machine, see this a direct input, this one is missing, right? So that's what the difference, that in a Moore machine that the next state combinational logic is applied to the state register and that portion of output again is feeding back to the input, right? But here there is no relation with the input and this output combinational logic, right? So based on that, either you can go for a kind of Moore machine model or a Mealy machine model, right? So again that depends on the kind of designer's wish, in what way he or she wants to design this kind of synchronous sequential circuits, right? Here you can see the difference between Mealy and Moore based FSM, where how in what way you can represent a Mealy machine and what way you can represent a Moore machine. So here you can see the first is output depends both upon the present state as well as the present input. That's what we have just seen in the block diagram. Same in a Moore machine, the output depends only on the present state. So generally it has fewer states than a Moore machine and generally it has more states than the Mealy machine, right? The value of output function is a function of the transitions and the changes when the input logic on the present state is done, right? But in a Moore machine, the value of the output function is a function of current state and the changes at the clock age, whenever the state changes occur, right? So Mealy machine react faster to inputs. They generally react in the same clock cycle. Why? Because here the direct input is provided to the output of the combinational logic, right? But in a Moore machine, more logic is required to decode the outputs, resulting in a more circuit delays. They generally react one clock cycle later, right? So that's what in a Moore machine, this is one of the drawback, that it will provide a kind of delay because the after clock it will change the states, right? Now in this particular section we are going to learn about how we can understand a kind of Moore machine, and in Moore and Mealy machine where you can have a advantage to reduce the number of states, right? So based on that we'll learn about the kind of state reduction. And here in this particular reduction in number of flip-flops, where if there are m number of flip-flops, the the required or produce the states are 2 raised to m. Based on that, if we directly go through and learn about this kind of design procedure, this is a kind of design step to make the reduction of this FSM. So step number 1, from the word description and specification of desired operation, derive a state diagram for the circuit, reduce the number of states if necessary, assign binary values to the state, obtain the binary coded state table, then choose the type of flip-flop to be used, and derive the simplified flip-flop input equations and output equations, and finally you can draw the logic diagram. So based on that, if you learn, see, this is one kind of state machine where A, B, C, D, E, F and G all are defined as a states. Like if you take 4 variables, you have a 4 state like 0 0, 0 1, 1 0 and 1 1, right? Based on that, here you have a states starts from A, B, C, D, E, F and G, right? Now again, this particular line shows that 0 is the input and 0 is the output. That does mean if you want to remain in a state, if you have applied 0 input and you get output 0, right? But this is not case with when the state is going to be changed from A to B. You can see when you apply input as a 1 and you will get output as a 0, right? Same way you can go through all this state diagram in our previous session. From the state diagram, how you can draw the state table. So this is a kind of state table where all the present states are given like A, B, C, D, E, F. Based on that, the next state and output based on x is equal to 0 and x is equal to 1, right? So this 0 comma 0, so first 0 input x, that states the next stage of A and B, right? That stays as x is equal to 0, and that's what the 1, if you see, that's x is equal to 1. So you can see here from the present state, next state and output, where next state in both the condition like x is equal to 0 and x is equal to 1. So here we have taken x as my input, and your output, again you are going to check when x is equal to 0 how the output is going to be behave, when x is equal to 1 how the output is going to be behave, right? So this all this are present state from A to G. So you can see the sequence from A, B, C, D, E, F and G. From this particular state diagram you can draw this particular state table, right? So when you can see the x is equal to 0, the present state is A, the next state remains the A, right? So this is 0 and output is also 0. So this is 0 and output also 0, you can see here. Let's say from B to C, or let's say again a kind of present state is A and that going into a B when x is equal to 1. So that is A, is this is B. So from A to B, see, x is equal to 0, your output again remains 0, right? By that way you can identify and go through and verify all this particular state diagram in terms of the state table, right? Let's say one more middle example we can take, like it changes from D to E when x is 0 and output is 0. So from D to E, see, x is 0 and output is 0. You can see this particular cursor. Last one is from G to A. You can see from G to A, your x is 0 and your output is also 0. From G to F, again from G to F, your x is 1 and your output is also 1, right? By that way you can define this representation. That's part that you already learned in our previous session, right? Now most important part is that how you make the reduction of this particular state diagram or state table, right? You can see here the present state is G, that is converted into A when x is equal to 1, that is converted into F when x is equal to 1, right? So again from G is converted into A when x is equal to 0, and G is converted into F when x is equal to 1, right? The same terminology you can see here when E is goes to A and when x is equal to 0, when E is goes to F state when x is equal to 1. So I can replace this particular G by only E, right? Because here E and G both are same. So here there is a redundancy of these two states. So there is no meaning to take the G further, right? So you can again see this particular E state is same as the G state. So I can consider E is equal to G here, right? Once you take E is equal to G, there is no meaning to take the last state which is a G state, right? So based on that you can see when you take E is equal to G, again where A and F is there. So here when F is equal to G and F, here G and F, you can take this G as a E. So F is based on F is again comes to E, right? And F is comes to F when X is equal to 0 and X is equal to 1 respectively. This is the same as the state of D. So again, in summary, I can remove the state F and state G as simple state D and state E, because these particular states are the same state. So based on that, I have reduced this particular two stages, like E is equal to G. So here I put, instead of G I put E. This becomes the state of D. So I can remove F which is equal to D, and I remove G which is equal to E. By that way I can further reduce the state table, and based on that again this state table is same as the upper one, right? So where I have reduced, because two states are nothing but the redundancy with each other, right? So based on that I have reduced it, and based on that particular reduced state table, say I can make this kind of reduced state diagram. Now what is exactly meaning of this? See, in first example, so in first state table you can have 1 2 3 1 2 3 4 5 6 and 7, total 7 states are there. But after this reduction you can have only 5 states. So if it is a 5 states, again it's a number of flip-flops, number of logic diagrams, number of wires you have reduced. Here you have not compromised with the output as well, right? So this is the best example of the finite state machine, Mealy machine or Moore machine, where ultimately you have reduced the state flow diagram, and based on that, see, all your criteria would be satisfied. That's how you can reduce this particular state table, right? Now assign this binary values to the states. So here we can define this all these values like this. These all are the states. Is like S0 is a state, S1 is also a state, S2 is also a state, and S3 is also a state, right? So how within a state this 0 stands for the input and this oblique 0 stands for the output, right? So based on that you can again draw this state table based on this state diagram, right? So this is how when S0 is changes to S1, see this particular arrow. So here 1 is the input and this particular 0 is the output, right? Again from S1 you can go to S0 with the input is 0 and output is 0, like that way. So based on that, once you follow this particular rule, you can assign here the kind of four state like S0 is 0 0, S1 is 0 1, S2 is 1 0 and 1 1. So based on that again you can put this kind of sequence detector, and based on the sequence detector, once you go with the state table of this particular sequence detector, you can see this is the present state like you consider as a S0. This is the next state like you consider as a 0 0, which is same as S0, right? With the input of 0 and output is 0. So that first state, this one will indicate like this one, S0 is 0 0. So it will again come to the same state again 0 0. Present state comes to the next state when input is 0. So when input is 0 and output is also 0, right? So here output is also 0, right? Same way if you consider the middle one, let's say 0 1, and that goes to the 1 0. So 0 1 is the S1 and that goes to the S2. See, 0 1 is goes to the 1 0. See, input is 1 and output is 0. So the input is 1 and output is 0. By that way, see, you can define this particular state table. Like let's say the last one, 1 1, it goes to 0 0. So 1 1 is goes to 0 0 when input is 0 and output is 1. So when input is 0 and output again is 1, right? By that way you can verify this particular sequence, and you can go through this. Now there are different kinds of flip-flops excitation table that you have to learn. What do you mean by the excitation table? Excitation table is nothing but that will give you the output in terms of the input. That means if you take any flip-flop, and now here you can take your output, and based on output you can select your input. So it's is the table of output to input. So that's C. Q of t is the output, Q of t plus 1 is your again output. So what kind of input you select such a way that you will get this kind of output. Same way for the t, same way for SR, and same way for a D. So if you want if you want 0 and 0 in a JK flip-flop output, If you want the output of 0 and 0 from the JK flip-flop, you have to apply 0 and X to the JK flip-flop as part of the input. Same way, if you want 1 1 in a output of T flip-flop, see, you have to apply 0 to the input of D flip-flop. Same way for SR and D flip-flop. So you must have to learn this, and you have to remember this excitation table. I can design counters, right? So again, I can design the counters or any sequential synchronous sequential machines or circuit design. So this is what the flip-flop JK flip-flop excitation table. Based on that, I can define this particular state table where A and B is a 0 0, X is 0 0, next state is 0 0. So based on this 0 and next state 0, so this is a QT, this is a QT plus 1 for A, this is QT for B, this is QT plus 1 for B, right? Based on that, I can assume this. So if A is 0 for a present state and A is 0 for a next state, you can say the for A flip-flop JA and K is 0 X. So that's what the 0 is. This is what the 0 is. So 0 and X you will get. So 0 and X you will get. Same way, 0 and 1. So this is a 0. This is a 0. Again 0 and X. This is a 1. And this is a 1, so 1 and 1, X is 0, so X and 0. By like that way, using the excitation table, you can also judge or you can also evaluate the flip-flop inputs as well. So excitation table is nothing but output to input table, right? So based on that, again, we use this kind of truth table here, this particular state table. From this state table, we use this particular sequence, like we would like to find here the Boolean function of JA, KA, JB and KB using the K map, and you already know this particular K map terminology, where you find JA is equal to B into X dash, KA is equal to B into X, KB is equal to A not X, and JB is equal to X, and based on that I can be able to draw the kind of synchronous sequential circuit based on this particular terminology, where it includes both Moore and Mealy machine, right? So how you can draw the design, or how you can evaluate the design: state diagram, state table, then you derive the equation of Boolean function, and finally you can draw the digital circuits. Same way, if I want to go for a 3-bit counter, I'll start with 0 0 0 and ends with the 1 1 1. So this is a kind of counter where its first count is 0 0 0, 0 0 1, 0 1 0, 0 1 1, like that way it goes up to 7. So based on that, I can use here T flip-flop, and based on the excitation table, this is the 0, this is the next state 0, and based on that you can evaluate our output, and this 0 you are getting from the excitation table. And once you go for T2, TA2, TA1, TA0 of the K map, see, you can design this particular 3-bit counter using the T flip. So by that way you can design a kind of synchronous counters using this particular design, right? Thank you, dear students. What we learn about here is Mealy and Moore machine, how we can design using all the procedures or step of this synchronous sequential circuits. Thank you very much, dear students.